All right, so we're going to be starting Unit 6, which is Gravity, Circular Motion, and Satellites. So our first part is Chapter 9, which is about gravity. So we're going to talk about the universal law of gravity, universal gravitational constant, how gravity and distance are related with the inverse square law. We might talk a little bit about weight, ocean tides, gravitational fields, what Einstein thought about gravity, black holes, and kind of, again, just summarize the idea of universal gravitation. So one of the big kind of misconceptions in physics, at least in storytelling, is that Newton got beamed off the head with an apple. That's how he discovered gravity. Well, first, he didn't discover gravity. Gravity was known about. What Newton figured out was this idea of gravity being universal. He was the first to realize that the same force that pulled an apple down from a tree or leaves off of a tree had to be the same force that was keeping the moon in orbit. All right. That's what they consider this idea of Newtonian synthesis, this idea that aha moment of gravity on planets was the same as gravity that acted on Earth. So the law of universal gravitation basically states that everything pulls on everything else. So the Earth is attracted to the moon just as the moon's attracted to the Earth. The Earth's attracted to the sun's attracted to the Earth. You're attracted to the Earth is attracted to you. Okay? So every body attracts with a force that's proportional to the masses and inversely proportional to the square of the distances separating them. Right? So as an equation, that looks like the mass of 1 times the mass of 2 all over the distance squared. But that's proportional to. All right? This is what he actually stated. This is what he discovered. So the more mass you have, the greater the force. However, the greater the separation distance, the weaker the force. All right? So like right now, you're attracted more to the Earth than you are to the sun. Why? Because you're closer to the Earth. Eventually, he realized he had to make it so it was equal, and he came up with this idea of a gravitational constant. All right, he didn't even take the time to find that gravitational constant, though another scientist by the name of Henry Cavendish did. And when Cavendish did the experiment, he figured out that G, that universal gravitational constant, was 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. All right, so once they had that value, they were able to calculate the mass of the Earth. They were able to calculate the mass of other planets, things like that, based on observations that they had made about some other factors. So again, universal gravitation is basically stating that everything attracts everything else. All right. So part of the reason the Earth is round is because of gravitation, because when it was being formed, all that matter that was forming it was being pulled on equally. All right. So stars end up becoming spherical for the same reason, because all the gases in the plasma are being pulled on equally. Okay. And one other thing we need to also note, though, is that the universe is still expanding and accelerating outward, because everything from the Big Bang is still going outward. So a quick check-in here. So the universal gravitational constant G, which links force and mass and distance, or force to mass and distance, is similar to which other familiar constant? To pi, to G, acceleration due to gravity, speed of uniform motion. So which of those is a constant? Like it never changes. The answer is pi, because the other things can change based on different factors. Gravity changes based on where you are on Earth. And we're going to discover, as we do this unit, that the attractive force, there's a reason that changes, if I'm on the top of a mountain versus at sea level. So inverse square law, if you notice, is that 1 over d squared relationship that's in the actual equation. So what this is telling us is the intensity of the effect is going to vary based on the inverse square of the distance of the cause. All right, so that means as the distance squared goes up, basically the intensity goes down as a factor of that. But the interesting thing here is it never will approach 0. Because even if I put 1 over infinity squared, it's not 0, it's just a very, very, very small number, not 0. So an idea of understanding this intensity piece. So gravity has a certain amount of intensity. Let's think of it in terms of paint. So I spray paint. I'm a unit of 1 distance away. So I get an area of 1. I'd have a thickness of 1 layer of paint. I go out to 2 now. Well, 2 squared is 4 areas. So 1 over 4, I'd have a fourth of a layer thick. If I go out to a third, a 3 here, right? So 3 times 3 would give me 1, 2, 3, 4, 5. So it would give me 9 areas. So that would become 1 ninth. All right. If I go out to 4, that would give me 16. That would give me 1/16. So just like the paint would get thinner and thinner and thinner, the force would get weaker and weaker and weaker and weaker, right? As I keep going out more and more and more distance away. So now we have an example of an apple. So the apple I know weighs 1 Newton when it's a distance of 1 basically radius or distance away from Earth. When it gets to 2 distances, it's at 1/4. What if when I get to 4, so when I'm out here, how much will the apple weigh? Well, it should be following that 1 over d squared relationship. So it should be approximately 1/16 of a Newton. If I get out here, this should be 1/25 of a Newton. All right. If I got out even further, it'd become 1/36 of a Newton, then 1/49 of a Newton, and we just keep following that squared relationship. So, another quick check-in here. The force of gravity between 2 planets depends on their masses and the distance apart, planetary atmospheres, rotational motions, or all of the above. Depends on their masses and the distance apart. So it's the masses multiplied together over the distance squared. Okay, so if the masses of 2 planets are each somehow doubled, the force of gravity between them should double, quadruple, reduce by half, reduce by 1/4. It should quadruple because I'd have 2 times mass 1, 2 times mass 2. Well, that would give me 4 mass 1, mass 2. Right? So that's quadrupled. So the mass of one planet is somehow doubled. The force of gravity between it and its neighbor is doubled, quadrupled, reduced by half, reduced by 1/4. It's going to be doubled because now only one of the masses was doubled, not both. So, real-world applications. Why would you care about polar gravitational forces? Okay. Biggest one we care about in New England, ocean tides. So every day we have 2 tide cycles, high tide, low tides, right? So every 12 hours we have a high tide. Every 12 hours we have, a low tide. Basically it goes, it's a 6-hour cycle. So high tide, low tide, high tide, low tide. So in that cycle, it's because the Earth is rotating on its axis. And the moon roughly, takes so long to go around the Earth, it's almost like it's staying where it is in the sky. But this unequal tug causes the bulge in the water, which is what causes the high tide. Now, what about this thing called an astronomical high tide? Well, there's spring tides and there's neap tides. So when we have a new moon or a full moon, we get the spring tide. And the reason for that is you get a pull from the moon and a pull from the sun in the same direction. Okay, so it's like you get 2 forces pulling this way. We get the astronomically high tides, as we call them, at the new moon and the full moon. Okay, and this gets really bad if we have a storm at that time because then you get all the extra beach erosion and all that. Now, if we're halfway between, we get the neap tide. So basically, these are the high tides that aren't that high and the low tides that aren't that low. And that's because the moon is this way, the sun is this way. So when I add the 2 forces, it's like one's this way, one's that way. So my vector net force is kind of at an angle. It's kind of weird. So it's like a more even tide for the month. It's not like it doesn't go as high, it doesn't go as low. It just kind of stays kind of even. But it still fluctuates a bit, obviously, because the moon has a greater effect than the sun does. And that's the neap. So, gravitational fields. So one way to view this idea of gravity interactions between like the moon and the Earth is the idea of a field. All right, because we're dealing with an action at a distance. So we think of the Earth as being surrounded by a gravitational field, the moon interacting with that field, even though the moon has its own field. And gravitational field is thinking of the space around Earth, or any mass for that matter, being altered. Another example of a field that you're probably more used to seeing is a magnetic field. So if you're a little kid, they probably show you a magnet under like a piece of paper and they sprinkle the iron filings on it. You see all the little field lines. That shows you where all the force lines are around that magnet. Well, very similarly for Earth, or any mass for that matter, field lines kind of radiate towards Earth because they're attractive force lines or field lines. So down here, where they're closer, that's because they're stronger. Out here, where they're further apart, that's where they're weaker. Okay? So the closer those field lines get together, the stronger you actually have for a force from that field. Part of the reason we like to represent with the field as opposed to just the single action, force pair is so that you understand that the force of gravity is kind of everywhere. It's not like it's just between you and the Earth. It's between anywhere around that planet, or like Earth, at that distance. That's the same kind of effect. That's the same kind of acceleration due to gravity or field, gravitational field. So if I was to plot that relationship of the pull of gravitational fields either inside a planet versus outside the planet, inside the planet you get some kind of odd behaviors because inside the planet you've got mass above you, mass below you, so you're being pulled kind of towards parts of the planet inside, parts of the planet outside. So when you're inside the planet, it's almost like a linear, nice, happy relationship. But then once you get outside, you get that nice exponential decay as it decreases towards zero, but never reaching zero. Okay? At infinity, it's not like you're at zero, but you've approached zero. So here's the little conundrum. What if I was to dig a hole through Earth and jumped in? Well, because that whole idea of this mass above you and below you, you'd actually end up kind of falling forever. Because like right here, the force would be kind of downward. You'd be a little bit less here, no force. You'd have, again, force pointing towards the center, and then a little more force. So constantly you'd be accelerating towards the center of the Earth. So you kind of like start to like alternate, going back and forth and back and forth and back and forth forever and ever and ever. And you'd be stuck constantly falling as you just pulled back towards the center, as long as you had sufficient speed and not too much air resistance slowing you down. So this gets us to Einstein's theory of gravitation. So Einstein, with that idea of those fields, he's thought of it more of like warping a surface. So think of like if you put a dent in a waterbed by putting a bowling ball on it, or if you just had a stretched sheet and you put a bowling ball in it, it would warp that space, okay? So his idea was, okay, well now if I put something in near here, if it was going at the right speed, it might just kind of gyrate or oscillate around here in orbit, all right? But if it wasn't at the right speed, what if I launched something in here and it was going too slow? Well, what might happen is it might spiral in and crash. And that's kind of like that coin fountain at the mall. You put the coin in, it slowly spirals down the little vortex because it's not going fast enough to maintain going around in an orbit. So it gravitates towards kind of that center deviation, that dent, we'll call it in space-time. Now, the cool application of understanding these, gravitational fields and gravitational effects is black holes. Because if a star shrinks enough and its mass is concentrated to a small enough radius, you can get to a critical point where you form a black hole. And all a black hole is this region of space around this collapsed matter where the gravitational field becomes so intense that even light can't escape. Because like we just said with that whole orbiting kind of around those dented parts of space-time, if that speed equals the speed of light or is greater than the speed of light needed to maintain or orbit, you're going to get pulled in. And even if light goes by, light's going to get pulled in. So you get these regions of space where literally all the light's pulled in, you can't see. That's why it's a black region of space or a black hole. So it's not like it's the color black, it just means you can't see the light there. So just to the example here, we're just following that Fg equals big G m1, m2 over d squared. Well, the radius of the star here is our d. And as d goes smaller, the force goes greater and greater and greater and greater and greater. So if I was to make this a quarter of the radius, I'd go up by, another factor. If I made it, a tenth of the radius, whatever it is, goes up by another factor. It just keeps going greater and greater and greater and greater until the force eventually is the point that even, again, light can't escape. So what would happen, though, if if the sun became a black hole? It would break away from the attraction of the sun, it would be pulled into the sun, it would become a black hole too, or none of the above? None of the above. It would actually just keep on orbiting, because the same amount of mass would be at the same distance from Earth, so there'd be no reason for us to get pulled in.